Dataset joining is going to be a crucial skill for your data analysis career, as it will allow you to combine information about the same entities from multiple different sources in order to facilitate more complex and more comprehensive analyses. In this lesson, we're going to look at how to do data joining using a number of verbs from the dplyr package. So let's go ahead and get started. So here is our list of learning objectives. If you like, you can pause the video and read through these, but we're going to come back to them at the end of the lesson. Let's start now by loading the packages needed for this lesson. The packages we're going to need are the tidyverse package here, the tidyverse package, and the country code package. So load those two packages. The tidyverse package is going to load, of course, dplyr, which contains the joining functions we're going to be learning about in this lesson. And so let's dive in immediately and start thinking about what exactly is a join and why do we need it. To illustrate the utility of joins, the usefulness of joins, we're going to start with a toy example, and we're going to use these toy examples a lot throughout this lesson. So here's our toy example. Consider the following two datasets, demographic and test info. So demographic is going to contain the names and ages of 3 theoretical patients, and we're going to define demographic using the tribble function from the tidyverse. Let's define demographic, and let's print that to see what the demographic dataset now looks like. So as you can see, we have these 3 rows, Alice, Bob, and Charlie, the name and the ages. The age is abbreviated by the R mark down here, but you can see the ages there, 25, 32, and 45. The next dataset we're going to define is test info, and this contains theoretical tuberculosis test dates and results for these same patients, Alice, Bob, and Charlie. You can think of them as A, B, and C. So let's go ahead and load that dataset. So again, you can see Alice, Bob, and Charlie, and they have these test dates in year, month, day format, and whether or not it was positive or negative. So let's go ahead and run that, take a look at the dataset, and verify that it is indeed a data frame of the form that we had expected. Now what we would like to do in theory is analyze these two datasets together. So we need some way to combine them, combine the demographic information for Alice, Bob, and Charlie with their test information. So let's think of how we can do this. One common option you might think of is the cbind function from base R. Now what cbind does is it just puts the columns right beside each other. It binds the columns to each other. So let's go ahead and try that here. So we do cbind, demographic, and test info. And here's the result. We have the name and age. And then we have again name, test date, and result. So think about it as it simply just takes this data set and this second one and puts them beside each other, kind of like Legos. But there is an important problem here, which is that the name column is appearing twice, which obviously is not ideal for your data analysis. And there's going to be other problems with this approach. For instance, what if the rows in the two datasets are not already aligned? So let's look at what I mean by that. Consider this other dataset, test info disordered. So now test info disordered, instead of ABC, Alice, Bob, Charlie, we now have Bob in the first row. So we define this dataset calling it test info disordered. Let's quickly print that to our console so we can see. You can see now that Bob is in the first place. And now what happens if we try to run this line that binds demographic to test info disordered? So the problem now is that everything in the first row got matched and everything in the second row got matched, irrespective of which person it actually pertained to. So Alice is with Bob and Bob is with Alice, okay? So this data is obviously combined incorrectly, and this is a naive approach to trying to fuse together these data sets. And we have a third issue with this naive approach of simply trying to stick together the data frames. And that is what happens when you have a one-to-many relationship. So let's look at an example to consider this. Consider that Alice did multiple tuberculosis tests. So consider this data frame now, test info multiple, where we have 2 rows for Alice. She was tested on 2 different days. We define that as test info multiple. And I'll just print that just so you can see again what that looks like as a data frame. Okay. Now what happens when we try to merge this with cbind? It's not going to work due to a mismatch in the number of rows. So let's actually try that and see. We do cbind demographic test info multiple, and it says argument implied differing number of rows. Now, as a side note, what we just demonstrated is a one-to-many relationship. That means we have one entity in one dataset, but multiple matched entities in the other dataset. And this is something we're going to consider in a future lesson. So now that you've seen these important details that you have to pay attention to conceptually when you're trying to fuse datasets, it should become obvious to you that we need a smarter way to combine datasets. And that brings us to the concept of joining. So let's start with the most common join, which we call the left join. So let's see how left join can solve our problems. In the simple case, when we had the dataset perfectly matched, left join is going to work right out of the box. So we go left join, and then our first argument is the demographic dataset, and our second argument is the test info dataset. And if we run this, we'll see that we have the perfect join, and now we don't have the name column duplicated. Okay? Now, how about in the case where the order is not the same between the two datasets, where we have the disordered data? So there we try to left join demographic with test info disordered. And if we run this, we can see again that the join worked perfectly. So Alice's information is still combined with the Alice's test date, and Bob's information is tied with Bob's test date. If you want, you can look at the original dataset to confirm that. And finally, in the one-to-many case here, it will work also out of the box. So left join demographic, and let's go test info multiple. And if we run this, again, we'll see now that there are now two Alice rows, and the information is still combined accurately. So hopefully you can appreciate the efficiency and the clarity with which we can fuse these datasets. Joining is a simple yet a powerful tool. Now, as a side note, for those of you who are familiar with piping, you can also use the pipe operator with left join. So for example, here we have demographic piped into left join test info. If we run this, this is equivalent, of course, to doing left join, comma, demographic, and then test info. So hopefully you recognize the correspondence between these two lines of code. So now you hopefully understand the why of data joining. Let's now take a deeper look at the how. Let's jump into the syntax of joining. So joins operate on two data frames, as you've already seen: the X data frame or the left data frame, and the Y data frame or the right data frame. And you can input these data frames either as named or unnamed arguments. So let's try both ways. We try the named approach and the unnamed approach. The named approach is we write left join, and then the first argument X equals, and we use what the datasets we defined before, X equals demographic, and Y equals test info. Okay, this is the named approach, and we run that and we see that it works. The unnamed approach, you just have to put the name of the dataset, and you allow R to infer that since this is the first argument, then it must be the X. And since this one is the second argument, it must be the Y. And if we run this line, it will also give us the same output. Another important argument is the by argument, and this indicates the key that we use to connect the tables. So sometimes it is not needed, like with our demographic and test info datasets. Why is it not needed in this case? Let's just print just the demographic dataset. We can see it has a column called name, and the test info also has a column called name. Because there's a common column to these two data frames, we don't need the by argument, but we can still provide it. So here, for the second option, I'm going to type comma by equals and then name in quotes like that. And if we run this line, we can see it gives us the same output. So it wasn't needed, but now we're going to see an example of when it is needed. The by argument sometimes is required, for example, when the keys are named differently in the two datasets. So let's see what I mean by that. We're going to define a new data frame here, and we'll call it something like test info different name. Okay, and what we're going to do here is replace the name variable with some different word, like, I don't know, let's call it a test underscore recipient. So if we run this and print out the tibble, we can see that name has been replaced by test recipient here. Now, what if we try to combine this test info different name with the original demographic dataset? Let's see what happens. Attempting to join these two data sets, it says, will lead to an error. Let's go ahead and try it. So we do left join, okay, demographic, and a test info different name. And if we just run this, it's going to give us this long error. But if you look at this line here that has the exclamation point, it says by must be supplied when x and y have no common variables. That is the most helpful error I've ever read in my life. It tells you perfectly what you want, what you need to do. So the problem here is that there is no obvious key, no obvious column that connects the two data frames. And to fix this, we either rename the column or we specify columns to join on using this by syntax. So how does the by syntax work? Let's try it here. We're going to do left join demographic, comma, test info different name again, and by equals C, which creates a vector. And it's going to be a word vector. It's going to be kind of a named vector where we have the name of the variable on the left-hand side first. In demographic, that is name. So here, name equals, and again in quotes, the name of the key in the right-hand side or the Y data frame. In that case, that's test recipient here. Okay. So if we run this now, you'll see that the join has worked successfully. So the syntax is a little bit weird, but what it says basically is tell R to connect the name column from data frame X with the test recipient column from data frame Y. So now you know how to use the first of the joining verbs, which is left join, along with the X, the Y, and the by arguments. So you are ready for your first practice question. So here is the practice question we want you to work on. It says left join patients and checkups. Consider these two data sets below. One has patient details, okay, for 3 patients, John, Joy, and Khan. And the other has medical checkup dates for those same patients. And we want you to join the patient's dataset with the checkups dataset using left join. So go ahead, pause the video, and try that out. And now here is another practice question that requires you to use again left join, but with the by argument. So here we have again 2 datasets defined below using the tribble function, one with patient details and the other with vaccination records for those same patients. So patient details is defined here with ID number, full name, and address, vaccination records with patient code, vaccine type, and vaccination dates, and you need to join those 2 datasets. Now notice that in this case you are going to need the by argument. Why? Because there's no common column that is an obvious key between these 2 datasets. So figure out what is going to be your by argument and work that out. Now that we've introduced you to the most common join, the left join, let's think about why are there actually multiple different types of joins. So in the real world, datasets often do not match perfectly. That is, we won't always have, for example, Alice, Bob, and Charlie in both of our datasets. Another way to say this is that not every row in one dataset will have a corresponding row in the other. So different types of joins handle these imperfect matches differently. We have 4 main types we're going to consider: the left join, the right join, the inner join, and the full join. Let's start with the one we've already seen, which is the left join. So left join is going to retain all records from the left data frame, even if there's no match in the right data frame. To illustrate this, let's revisit the demographic dataset and a modified version of the test info dataset. So to refresh your memory, let me print out both the demographic and the test info datasets. So here's demographic with the name and the age, but the age is abbreviated by R Markdown. It's a bit annoying. And then we have the test info dataset with name, test date, and result over there. So what we're going to do is we're going to remove Charlie from the test info dataset and add in a new patient called Xavier. In doing that, we're going to define a new dataset called test info Xavier. Okay. And notice now that we no longer have ABC, Alice, Bob, Charlie. We now have Alice, Bob, Xavier. And this is going to help us illustrate how left join works and how it's different from the others. And let's go ahead now and see how left join is going to work in this context. So we're going to perform a left join using these two datasets. So left join with X being the demographic dataset. Left join X equals demographic, and Y equals, instead of test info Charlie, we're going to use test info Xavier, or that is, instead of the regular test info, we use test info Xavier. And now take a second to think about what is going to happen to Charlie and what will happen to Xavier. If you don't understand that question, let me quickly print out these two datasets to the display again for you to see. So the demographic dataset has Alice, Bob, and Charlie, okay? And the test info dataset has Alice, Bob, and Xavier. And we're trying to fuse these two datasets to combine the information about Alice, Bob, Charlie, and Xavier. But of course, Charlie and Xavier cannot be matched because they're not both in the two datasets. So again, I ask, what will happen to Charlie and what will happen to Xavier? Let's go ahead and see by running this line. So as we can see here, Alice, Bob, and Charlie remain in the output dataset, but the information for Charlie in terms of test date and result is left as NA, that's not available, because that information was not present in the test info Xavier dataset. So just as I already said, Charlie is retained with NA values for test info, and Xavier has been discarded. How do we understand this behavior? Well, basically, in this code left join demographic test info Xavier, all records from the left data frame, that is the X data frame, or the first data frame presented here, demographic, were retained. Now, hopefully this is intuitive for you. We're working with a left join, and therefore the records from the left data frame are retained. Those records are prioritized. Those records are not dropped even if they have no corresponding match in the right data frame. So left prioritizes the left. Now here is a visual representation of how the left join works. So we're going to wait for it to play again. On this left-hand side, we have the demographic with name and age, okay? And on the right-hand side, we have that test info dataset with name, test date, and result. The left-hand side has Alice, Bob, and Charlie, ABC. The right-hand side has Alice, Bob, and Xavier, ABX. And notice that when we join only this, of the two between Charlie and Xavier, only Charlie is kept in the dataset. So the left join makes sure to keep in the final output everything that was in the original left dataset. So left join again prioritizes the rows from the left dataset. Now let's consider what happens when we switch the left and the right datasets in left join. Okay, so now we're going to perform a left join with test info Xavier as the left data frame. So left join X equals, instead of demographic, now we have test info Xavier, and for the Y dataset we have Y equals demographic. And now take a second to think about what's going to happen when we run this function, when we run this line of code. Is Charlie going to be kept in the output, or is Xavier going to be kept in the output? So when we run this line of code, we can see that it's Alice, Bob, and Xavier that are kept. So Charlie has been dropped. Hopefully this behavior is intuitive to you, okay? So now Xavier's data is included and Charlie's data is excluded because, again, left join has retained all the rows from the left dataset, which in this case now is test info Xavier. Here is a small piece of vocabulary for you. The primary dataset is the main or the prioritized dataset in any join. So in the left join, the left dataset is the primary dataset, and the other one is the secondary dataset. With all that information in hand, here is another practice question for you. Left join diagnoses and demographics. So try out the following. You have two datasets again here defined with Tribble, one with disease diagnoses and the other with patient demographics. And we want you to left join to merge these datasets, keeping only patients for whom we have demographic information. So far, we've been looking at tiny toy examples. Now we're going to try to analyze some real data. Consider the following example. We're going to be analyzing TB incidence, that's tuberculosis incidence, and government health expenditure in 47 African countries. So we have data on TB incidence rates per 100,000 people from the WHO Health Observatory, and we can read that in as TB 2019 Africa. This is specifically from 2019. So we can run these two lines of code, okay? And we can see we have the country, we have CA, which is cases, but abbreviated by our markdown, and we have the 95% confidence interval. Let's look at the next data set. Here we have data on health expenditure per capita from countries around the world, also from the WHO. So this is not just from African countries. Let's look at that. We call it Health Exp 2019. We read that in and we take a quick look. We can see we have country expenditure, and this is in US dollars. Now imagine that the analysis we're doing is that we want to see how TB incidence varies with health expenditure, specifically in African countries. Based on this information, what dataset should be on the left in our left join? Think about that for a second. Well, I think that we're going to want to put TB 2019 Africa as the left data frame to ensure that all African countries are included in the final dataset. So let's go ahead and code that up. We're going to use TB 2019 Africa as our left data frame, and here we're using the pipe syntax. So we'll pipe that into left join where it sticks in as the first argument, and the second argument is going to be health exp 2019, and we can call this combined dataset TB health exp joined. Okay, joined, and let's print that after we define it. Okay. So now think about what is going to be the output of this join. How many rows are there going to be in this join? Well, if we run this, we can see that there are 47 rows in our output because there were 47 rows in TB 2019 Africa, and we wanted to make sure to keep all those rows and not keep the rows that aren't matched in the right dataset. So left join prioritized the rows from the left dataset. So like I said, 47 rows were retained for the 47 African countries. Now what we should do next is check if there are any countries in TB 2019 Africa that did not have a match in Health Exp 2019. And the way we're going to do that is we're going to filter for any NAs in the expenditure column. Okay, hopefully that makes sense. So we take this TB Health Exp joined, and if there are any rows where the equivalent dataset couldn't be found in the right, in the expenditure, then expenditure will be NA, will be missing for those specific rows. We can see one such row here is Mauritius. So Mauritius, for some reason, was not in the health expenditure dataset, but we can do it formally by filtering is.na on expenditure USD. If we run that, we see now that there are three countries, Mauritius, South Sudan, and Comoros, that did not have a match in Health Exp 2019. And because our goal was to analyze the relationship between cases and expenditure in these 47 African countries, it is important that we know that there are three countries where we don't have that data. So in such a case, you would go ahead and try to find that data somewhere else, or you would just keep in mind that you're no longer analyzing 47 countries, you are now analyzing 44 countries. So again, because the focus was on the 47 African countries, we made sure to put that as our left dataset. Now here is a practice question for you using real data from a realistic analysis scenario. So it says, copy the code below to define two datasets. The first, TB cases children, contains the number of TB cases in under 15s in 2012 by country. And we get it from the tidyr package, which comes with tidyverse. Okay, and you run that. And then you have a country continents from the country code package, which lists all countries and their corresponding region and continent. Let me run that just so you can see what that looks like. So you have the country, the continent, and the equivalent region. Now what we want you to do is to add the continent and region data to the TB cases dataset. Okay, so think about which dataset should be your left data frame, and which should be the right, and then go ahead and join them appropriately using the left join. Now that you're comfortable with the left join, which is the most common and the most useful join, let's now look at the right join. So the right join is kind of like a mirror image of a left join. And in particular, the right join is going to retain all the rows from the right dataset, while left join retains all the rows from the left dataset. So let's look at a toy example using the demographic and test info Xavier datasets. So recall these two datasets. We have demographic with Alice, Bob, and Charlie, and test info with Alice, Bob, and Xavier. Now let's use right join with demographic as the right data frame. So since demographic is the right data frame, then the left data frame in this case will be test info Xavier, and the right data frame is demographic. Okay, and think about what we're going to see in the output. So let's run it. So as we can see, Alice, Bob, and Charlie are kept in the output data frame. What's going on there? Okay, so like I just said, all rows from demographic, are kept, and only matching records in test info Xavier are kept. So only Alice and Bob from test info Xavier are kept, but Xavier is actually discarded. So what is going on there? Hopefully you have an idea. Right join is prioritizing the data set that is on the right. In that case, this demographic. Okay, so here we have x equals, and y equals, just so it's super clear. And right join is prioritizing the rows that come from the right in this case, which is Alice, Bob, and Charlie. If we were to swap this and put x equals demographic, and y equals test info Xavier, think about what we would see in this case. Well, in this case, test info Xavier, which is on the right, will be prioritized, and Xavier is kept in the output rather than Charlie. Now here is a graphic to illustrate the right join process. Here what we're doing is right join with x equals test info Xavier and y equals demographic. And as you can see, the thing on the y, or the right data set, is prioritized, right? So Charlie on the right is prioritized over Xavier in that join. Now it's important to note that the same final data frame can be created either with left join or with right join. It simply depends on the order of your data frames. So let's see what we mean by that. We can have right join test info Xavier and demographic here on the right, or we can have left join with demographic on the left and test info Xavier on the right. So here, right join will prioritize demographic, keeping all rows from demographic. Left join will prioritize demographic, which is now on the left, keeping all rows from there. Okay, so right prioritizes the right, left prioritizes the left. We run these two lines and see that they're the same. This first line gave us Alice, Bob, Charlie. This second line here also gives us Alice, Bob, and Charlie. There is one small difference between the outputs of right join and left join. If you notice, when you do a right join here, we have name, test date, result, and then age. With left join, you have name, age, test date, and result. So the actual order of the columns is slightly different, but you don't really have to think about that. Like I write here, the column order may vary between left join and right join, but columns can be rearranged, so we don't really need to worry about their order. Since left join and right join can both give you the same output, you may wonder which one you should use. Well, data scientists typically prefer left join over right join because the logic is generally clearer and it is less error prone. So it makes sense for the primary dataset to come first in your function. That's the case with left join. Left join x equals the primary dataset. That first dataset is the one you care most about. But with right join, the one on the right, the second dataset, is the one you care most about. That's the primary dataset for right join. And that's a bit confusing, and it especially doesn't work with the piping flow. So in general, you'll want to stick with left join over right join. And in the spirit of favoring left over right join, We don't have any practice question for right join, so for now just ignore it. There are specific conditions where it will be nicer to use the right join, but by the time you need it, you'll know what to do. With left and right join now understood, you are very close to mastering most of all you need to know about joining. There are two other joins we'll consider, inner join and full join, but the principles there are pretty clear. So let's take a look first at inner join. So inner join is going to keep rows that are common to both data frames. Okay? And to understand this, we're going to revisit our toy example again with patients and their COVID test results. So we're going to use demographic again and test info Xavier again. So think about what the result is going to be when we use inner join on demographic and test info Xavier. In particular, notice that only Alice and Bob are in both datasets. So let's try it. Inner join, whoops. And then we have demographic as our left, and test info Xavier as our right. And if we run this, what we can see is there are only two output rows, Alice and Bob, because those are the only two that are common to both of those datasets. So Charlie was only in the demographic dataset and Xavier was only in the test info dataset, and therefore they were both removed. And importantly, the order of datasets in inner join does not affect the result. This is going to be the case with both inner and full join. The order of datasets does not affect the result. So here we had inner join, demographic, and test info Xavier. And here below, we're going to type the mirror image of that, inner join, x equals test info Xavier, and y equals demographic. And we'll see it gives us the same result, okay, with just Alice and Bob. There is a difference again in terms of the order of the columns, but that's not really something you have to think about. So here's a practice question for you on inner join. So the following two small data sets are about foodborne outbreaks in the US in 2019 from the CDC. Okay, so copy that code to define them. You have the total number of infections and the outcomes of those infections. And you want to use inner join to figure out which pathogens are common between the two datasets. Obviously, you can figure out which pathogens are common just by looking at these two datasets, but this is a toy example and you should do the practice anyways because that'll give you the principles for the real data when you get to it. Now for a real data example of inner join, let's return to our health expenditure and TB incidence rates data. That's TB 2019 Africa and Health Expenditure 2019, okay? And we're going to try to create a new data frame called inner exp TB that retains only countries present in both datasets. So let's go ahead and do that. So we have TB 2019 Africa inner join with Health Expenditure 2019. Now think about how many output rows there are going to be in this dataset. Remember that in TB 2019 Africa, we had 47 countries, and 3 of them were not matched in the health expenditure dataset based on our previous examples. Okay, so if we run this now, we can see that there are 44 rows because those 3 countries that were not matched in the health expenditure are dropped. Now here is a practice question for you. This is your second to last practice question. The code chunk below filters the health expenditure 2019 dataset to the 70 countries with the highest spending. So we just run this just so you can see that. All right. So we have 70 rows and these are the countries with the highest spending. And we want you to use an inner join to join this highest exp dataset with the African TB incidence dataset. Now, if you do this correctly, there will be just one row returned. Think about and write down why there's only one row returned from that inner join. Now, last but not least, we have the full join. The full join retains all records from both datasets. So if there are missing matches between the datasets, the function will just fill in the NAs. Okay? And we can demonstrate this with the demographic and test info Xavier datasets. So I won't print this again because I know you know what they are. Demographic has Alice, Bob, Charlie. Test info has Alice, Bob, and Xavier. Let's go ahead and do a full join with demographic as our X and test info Xavier as our right or our Y. Okay. And as we can see now, we have Alice, we have Bob, we have Charlie and Xavier, everyone together, one big happy family. And the NAs for the missing matches have been implied there. So as you can see, all the rows are kept preventing information loss. So this is the most inclusive of all of the joins. So the order of the datasets again does not affect the retained information, although it does affect the order of the columns. So instead of full join demographic test info Xavier, we could have full join test info Xavier demographic, and it'll be the same thing. We'll end up with the same 4 rows, but the order of the columns is slightly different. Okay, but again, you don't have to think too much about that. And to wrap up the visualization, here is a simple GIF showing you how that full join works. Okay, so here we have full join with the X or the left being the demographic and the Y or the right being the test info Xavier. And as you can see, when you join, you keep in all of the rows and you just put in NAs, missings for the unmatched spaces. Now here is a practice question for you, full join on malaria data. I won't read through it, but you can basically see that you have 2 data sets, malaria incident and malaria deaths, and you want to use a full join to retain all the information from the 2 data sets. So go ahead and try that out. Now let's do the real data example of a full join using TB 2019 Africa and a health expenditure 2019 of a range of countries there. So we're going to run full join. Let's do it full join here and create a new data frame called full TB health. So let's do that. We have TB 2019 Africa full join with health exp 2019, health exp 2019. Okay, and we assign that to an object called full TB health. And think about how many rows there are going to be in this output data frame. So when we run this, we can see there are 188 rows, even though the health expenditure 2019 had only 185 and TB 2019 Africa had only 47, because there are some rows in there that are not matched. So the final output is larger than either of them, similar to with the test info Xavier and demographic. Each of those had 3 rows, but when you joined them, then you end up with 4 rows in the output. So you can actually end up with more rows in the output than in either of the data frames. Now, before I let you go, here are 4 Venn diagrams often used to explain the concepts of joining. So with the left join, everything from the left set is included. Okay. With the right join, everything from the right set is included. With the inner join, only the things that intersect between the 2 sets, only the common rows between the 2 sets are included. And with full join, everything in both sets is included. So now let's go through our learning objectives to see if you understood everything that we aimed to help you understand. Firstly, we hope that by now you understand how each of the different dplyr joins work, the left, the right, the inner, and the full. And something to mention here is that this vocabulary, left, right, inner, and full, is not specific to just R, okay? In SQL and really in any other programming language that deals with data, these concepts are the same. These concepts apply to all of those domains as well. So hopefully you understand those clearly. Now, secondly, hopefully you're able to choose now the appropriate join for your data set. Wink, wink, the appropriate join is almost always a left join and sometimes a full join. And hopefully you can apply all these principles to join simple data sets together using functions from dplyr. We have the word simple there because there are a few more, slightly more complex joins we will discuss in a future lesson. So congrats on completing this lesson on joining datasets. With the functions you have learned from dplyr, you are now equipped to combine datasets in powerful ways to answer more complex questions. In the next lesson, we're going to dig into one-to-many joins and some special cases in joining as well. I'll see you over there. Bye-bye.